Hello everyone. We'll start with the subject fluid mechanics. So to begin with, we have the first outcome to summarize the fundamental properties of fluid. So we'll see what is fluid continuum and other properties of the fluids. So fluid mechanics is what mechanics and fluids. We'll see one by one. What is mechanics? We know that it is the study of forces or effect of forces or predicting the effect of forces. All about forces is known as mechanics. What is fluid mechanics? Fluid mechanics is the study of the response of fluids under the action of a variety of forces. So how the fluid behaves under the action of different kinds of forces is known as fluid mechanics. If the fluid is at rest, then the study is known as fluid statics. The study of fluids at rest is known as hydrostatics. The study of gases at rest is known as aerostatics. Study of geometry of motion of fluids with respect to time is known as fluid kinematics. Here, velocity components, acceleration components, and the pattern of flows are studied. Here, the force causing the motion is not coming into analysis. That's why it is fluid kinematics. Study of motion of fluids along with the energy and forces causing the motion is known as fluid dynamics or fluid kinetics. Fields of application of fluid mechanics are hydraulics, aeronautical engineering, chemical engineering, geology, meteorology, etc. Here we'll see how fluids stand different from solids. In solids, if we look at the molecular arrangement, it is very tight and relative motion of the molecules is not possible in solids, whereas liquids, the molecular spacing is more, relative motion of molecules is continuously occurring. So is the case in gases too. We know that any existing substance in nature can fall under one of the three categories, that is solids, liquids, and gases. The phase of existence is attributed to the distance between the molecules, force between the molecules, relative movement of the molecules, and resistance to the applied force. If you analyze, distance between the molecules is least in case of solids. In case of liquids and gases, it is much more. Force between the molecules is quite large in case of solids. It is quite less. In case of liquids, it is it's not there. In case of gases, relative movement of the molecules, it's not there here. It is there in the sense molecules move one with respect to the other continuously. And also in gases, resistance to the applied force. Here there is a large resistance which is known as the shear strength of the solid. Here hardly it possesses any shear strength. That is to say, any molecules can be easily pushed off with respect to the other molecules, both in liquids and gases. So solids do not flow. The solids have their own shape and size. They possess resistance to tensile, compressive and shearing forces. The particles are very tightly arranged without any movement between them. Fluids are the substances which are capable of flowing. Fluids flow. Fluids deform continuously under the shearing stress. Liquids and gases together are referred to as fluids. Again, there is a bifurcation between liquids and gases. Liquids are incompressible fluids, whereas the gases are compressible fluids. Liquids take the shape of a container and they have a fixed volume. Hardly there is any tensile strength. They almost do not have any shear strength, but resist compressive force if confined in a container. The characteristic property of liquids is they always have a free top surface. The gases expand to the given volume and shape, and they are compressible. They are compressible fluids. The volume of gas depends on the pressure and the temperature of the gas. So in further discussion, we'll cover mass density, specific weight, specific gravity, specific volume, and fluid is a continuum. So what is fluid? The term fluid is used for any substance in liquid or gaseous state or phase. The examples are water, air, oil, ink, milk, coffee, bitumen, tar, mercury, smoke or vapor, gases. All these things are examples of fluids in general, and some of them are liquids and some of them are gases. Fluids will undergo continuous deformation when subjected to shearing forces, and the deformation will continue till the force exists. It acts as if in layers. So this is the stationary boundary, and then you apply some force on the top surface. The top layer moves much more compared to the layers which are nearer to the stationary surface. If you look at this particular thing has moved quite large compared to the layers which are there nearby. But in actual, there will be molecules which will be in close contact, and then whenever a force is applied on the top surface, the top layer of molecules move much more compared to the molecules which are nearer to the boundary, or almost there won't be any movement for the particles which are there here. But the point to be noted here is, in case of solids, when a force is applied, depending upon the flexibility or elasticity, it moves a little bit and then develops a resistance and stays there. But in case of fluids, as you apply force, it continuously deforms till it gets failed. Fluids are treated as continuum so that a theory can be developed. So here, the method of considering fluid as a continuous mass is stated as continuum principle. Except in dealing with rarefied gases, all normal fluid mechanics analysis deals with the fluid as a continuum. I'll try to explain here. Solid, there is particles and then there is a space in between. In case of liquids and gases, it is something different. For example, here the distance between the molecules is there, but in between the molecules there is large space which is available. Where there is no liquid molecules, it is void. In case of gases also, the gas molecules are present and then there is a space between them which is where there is nothing. So microscopically, if you look at water, water molecules are there and in between the molecules there is nothing. In this picture, if you see in the upper region, the molecules are there, but distance between the molecules is large, and then there is a space which is between the molecules, which is a void. As you come down, the distance between the molecules is decreasing. It is quite compact here, but still there is a space between them. But whenever a theory is applied or the law is applied, it is assumed that the gas is fully present everywhere. There is no gap as such. Even for liquids also, there is no gap as seen here. In actual practice, it is there, but it is assumed that liquid will come in full. There is no gap. So this presence of a material in continuous space is known as continuum. So it's an assumption, but because in actual practice it is not so. There is a gap. So to express this, the average distance between the molecules is measured. If average distance between the molecules is lesser, then the resistance offered will be more, and if the average distance between the molecules is larger, obviously the resistance offered will be quite less. So one of the basic properties of fluids is its mass density. We know that mass is the property of any material because of virtue of existence. Any material will possess what is known as mass. It is not weight, it is not volume, it is not temperature, it is something that you cannot explain, just it is there, and it is known as mass. It is measured in terms of grams or in kilograms. The mass per unit volume is known as density or mass density. In case of solids, mass per unit volume is much more compared to liquids and gases. And liquids and gases, if you compare, the gases have got quite less density. So if you compare here a haystack on one side of seesaw and then here only a few bricks, right? The mass of this whole thing, big volume, is equal to mass of very small compact bricks. So this is a balance which measures mass. When you place a object on top of it, this measures how much is the mass indirectly. Here there is a kilogram of mass, or it is generally referred to as weight stones, but this measures mass indirectly because of its force on the surface. Mass density, which is represented by rho, is defined as mass per unit volume. The total mass divided by total volume gives mass density. Because of this, we can always calculate or find the mass as product of volume of the substance multiplied its density. Note the density of water, which is represented by rho with the suffix W, is equal to 1000 kg per meter cube. And if you simplify the units over here, you can see that it is 1 gram per cc. So 1 gram per cc or 1000 kg per meter cube is nothing but density of water. Here we'll see specific weight. First of all, what is weight? Weight is gravitational force or gravitational pull towards the center of Earth. Obviously, it is along the plumb line or whatever we refer to as vertical. Weight is always measured in terms of Newton or kilonewton. If we use the capital N, Newton is the scientist, and this Newton is a unit of measurement of force. Now, the weight per unit volume is known as specific weight or weight density. Now, when you place a substance over here, this measures the weight of an object. So, weight is nothing but a force which acts vertically downwards. So, this will also possess some weight. These bricks will also possess some weight. So, weight has got a direction as well as magnitude. That's why weight is a vector quantity, whereas mass is a scalar quantity. Now, what is meant by specific weight? It is represented by the letter gamma. So, weight to volume ratio, that is total weight divided by total volume, or it is defined as weight per unit volume. And therefore, weight can be calculated if you know the volume and specific weight. And here you can note that specific weight of water, that is gamma with the suffix W, is equal to 9810 newtons per meter cube, or it can be put as 9.81 kilonewton per meter cube. We'll see specific gravity. By definition, it is the ratio of density of any material to density of standard material. So it is a ratio. So density of one material you want, specific gravity you want, you keep the density on the numerator, divide by density of standard liquid, which is nothing but water. The ratio is known as specific gravity. So by this expression we can say that density of anything is equal to specific gravity multiplied by density of water. So one has to note here, specific gravity is also known as relative density, or RD. Now, specific gravity can also be defined as the ratio of specific weight of any material to specific weight of standard material, water. So S is equal to gamma of material divided by gamma of water. Now by this I can write specific weight of anything, any material, is equal to specific gravity of that material multiplied by gamma of water, or specific weight of water. One more definition, specific gravity can also be defined as the weight or mass of some volume of a material to the corresponding weight or mass of the same volume of standard material, that is water. In these two definitions, we have 1 meter cube. Here also 1 meter cube. 1 meter cube of water, 1 meter cube of material. Here also per meter cube, per meter cube. Now note down that the specific gravity of water is SW, which is equal to 1.0. This hasn't got any units because it is a ratio of the same property, that is density and density. Both of them are featured in same units because that the units cancel off, and resultantly you will not have any units as far as specific gravity is concerned. Specific gravity of mercury, if you take Sm, it is equal to 13.6. Next we have specific volume. So as per the definition, it is defined as the volume per unit mass. So obviously it is inverse of mass density. You can see here specific volume denoted by V with a score on that is equal to 1 by rho. The density is measured in kg per meter cube, whereas specific volume is volume per unit mass. That's why it is 1 by rho. For water, the specific volume can be put this way. It is 1 meter per 1000 kg, or it is 10 raised to minus 3 meter cube per kg. If you adjust the units, it can be seen that it is 1 centimeter cube per gram of water. So that is specific volume. Okay, thank you.